Am I audible? So thank you. So I'm going to talk about quantum mechanics of Plancherel growth, which is based on this work with Argho Chattopadhyay, Shubhankar Datta and Debanshu Mukherjee. So here's a brief outline of my talk. So I'll talk about the Plancherel growth process and the limit shape theorem. And the first goal of our work is to understand this Plancherel growth process from a matrix model perspective. So I'll write down a partition function for the Plancherel growth process, and then we'll see how doing the saddle point analysis of that partition function.
Can you tell me to just assume their mics? That's what the whole thing was about. They cannot. Oh, I see. So we keep silent. Sorry. Sorry, cannot use their
Okay.
mics. That's right to the
Okay. So we'll see that doing the saddle point analysis of that partition function, we can get a cleaner matrix model way of proving this limit shape theorem. Then our next goal is to study the fluctuations about the limit shape. So I'll talk about the quantizations of the fluctuations, and then I'll talk about something which I'll call as a state diagram correspondence. So let's start with the crystal growth process. So at any stage of a crystal growth process, a new particle always joins at a place where its energy will be minimum. So if you look at the upper layer of this crystal, there are various minimas. So a particle can join at any of these minimas, and if I label all the incoming particles by colors, then after a certain point, when you observe the crystal, it will have a particular shape, but depending on which colored particle joins where, it can have different colored configurations. So you can think of this color as a microscopic variable of this system, and the shape of the diagram as a macroscopic variable. Similarly, here is a figure for the 2D crystal growth. So I can label the incoming particles by putting numbers on them, and if I make sure that as the particles fall, they only fall in the increasing order of their labeling, then what we'll get is some sort of a standard Young tableau. So this kind of growth processes have been studied in the context of Young diagrams. So this is how the growth process of a Young diagram looks like. We can start from the 0 box, and then we can keep on adding a box at each stage to get a Young diagram with more and more number of boxes. So at any diagram at level k can be obtained by adding a box at a Young diagram at level k minus 1. So
level is the number of boxes of the
yes, level is the number of boxes. So Plancherel growth process is a particular kind of this growth process where there's a probability associated to each of this Young diagram, which is given by this Plancherel measure, and a Young diagram at level k, which I am denoting by lambda k, is obtained from lambda k minus 1 by this transition, by addition of a single box according to this transition probability. So this is a Markovian growth process, and the probability associated to each diagram is consistent with this transition probability. So this statement will be clear from this figure. So if I assign the transition probabilities, this is how the growth process looks. Now if I pick up a random Young diagram, then you will see that for a particular Young diagram, there are various paths leading from 0 to that diagram. So if we add all the probabilities associated to each of the paths, then the probability associated to that diagram will be exactly same as the Plancherel measure.
Could you show the probability for going from one diagram to the other again?
Yeah.
That dim means what, please?
The dimension of the Young tableau.
The dimension
of the representation corresponding to the
SUN representation or SN?
SN. Yes, so it is equal to the number of standard Young tableau. So what Vershik-Kerov and Logan-Shepp had showed that Young diagrams following this Plancherel growth process converge to a universal diagram as we go to the large number of boxes. So as the number of boxes becomes very large, to look at the shape of the boundary curve, we have to rescale the diagram. So what we do is we rescale it horizontally and vertically by a factor of 1 over square root k, so that the boundary becomes smooth under scaling and it takes a particular form which is known as the limit shape. So here's the explicit expression for this limit shape.
Sorry, that transition rule, could you motivate it, please? Where did that come from? Could you go back?
So it's so.
Why did you choose dim lambda k by 1 by k?
So
presumably this sums to 1, right?
yes, this sums to 1, that follows from the, because this dimension is the number of standard Young tableau, and if we add all the, if we take a square and add all of those, it turns out to be 1. So so the motivation is, it can be understood in this way. So the growth process of Young diagrams is a random growth process. So we would like to associate a probability which does not depend on the history, like it should be some sort of a transition probability which makes this process random. Like it should not depend on how we started, or at a particular stage. If I am looking at a Young diagram at level k, then it should not depend on what was the, like how did I come from 0 to k or k minus 1. So yeah, so that.
Why did, to start with, why did you want p lambda k to be dim lambda k squared?
This probability measure is associated to, so this is even apart from the context of this growth process, this probability is associated to the representations of any general linear groups, the compact groups. So this Plancherel associated it long back to the, he associated this measure to the representations of general linear groups long back, and then Kerov showed that if we assign this sort of a transition probability which is actually Markovian, then these two probabilities are consistent.
I see. So it need not be that probability came from some Markovian transition.
No.
It just so happens.
But this
Yes.
is a process that leads to that.
Yes, this is a process that.
So it's a little like Monte Carlo and Bose-Einstein, Bose-Einstein, thermodynamics. Monte Carlo leads to thermodynamics.
Yeah,
Does the sum of the probabilities add up to 1?
Yes, the probabilities do add up to 1.
I see. So this is not the permutation symmetric group, it is the SUN group, or?
So this is the permutation. So if you consider any Young diagram, so you can think of it as a representation of Sn, because any Young diagram with k boxes is a representation of Sk.
For instance, for S3, there are 3 representations
Yes.
whose dimensions are 1, 1, and 2. So 1 squared plus 1 squared plus 2 squared is 6 factorial. Is 6.
Siddharth,
Yeah.
I think it's just a great orthogonality theorem, nothing more.
The what?
The summation, it's a great orthogonality theorem. Summation of all the inner dimension square divided by n factorial, that should be 1.
You're more knowledgeable than me, Rama. I don't know this theorem, but okay.
No. What I'm saying is like take k to be 3.
Yeah.
Okay. You can have horizontal 3 box, vertical 3 box, and mixed representation 2, 1.
Yes.
Okay. The horizontal and vertical are 1 dimension and permutation group,
Yes.
and the mixed representation is 2 dimensional.
Yeah.
So if you add 2 squared plus 1 squared plus 1 squared,
Yeah.
you get 6.
Yes.
Divided by 3 factorial is 1.
Yes.
So that is nothing but great orthogonality theorem. That's all I'm trying to say.
Perfect. Thank you.
Is there a way of thinking about this probabilities in terms of Hilbert space? Say I say that I want to look at the Hilbert space as direct sum of all the representations coming from k boxes. And let's say
Yeah, we'll look at the Hilbert space.
and then say I want to choose one state. What is the probability that that state is coming from the representation lambda k? That will have a probability.
Yeah, but I'll talk about the Hilbert space.
So just, sorry, another context where I come across this word Plancherel. This is actually in the context of continuous groups, but it is some canonical measure that you associate to the space of representations,
Yes.
so that the space of representations is dual to the group. So it's a natural Fourier transform
Okay.
of group and the representations, and this measure is the one that does it. So for finite group, it must be that for SK. So that's the great outcome.
Yeah, this is the measure for the group theory.
Okay.
And Haar measure, dual to Haar measure.
Okay. So we come to the first goal of our work. So we would like to write down a matrix model which captures the growth of this.
Just before, she said something about some scaling. Could you go back to that, please?
Yeah. So as we are talking about the large k limit, k goes to infinity limit, so the Young diagrams become very large. So to see the shape of the boundary, we have to rescale the Young diagram. So what we do is we just rescale it vertically and horizontally by a factor of 1 over square root k to look at the shape.
1 over square root. I see. And how is that? Sorry, I don't understand how is that a Young diagram, please?
Oh, this sorry, I forgot to tell you. So this is in the rotated notation. So if you take the usual English notation, yeah, just. So you can. So this is a Young diagram in the is what is called as the French notation. If you rotate it by 45 degree, you will get this sort of a diagram. So we usually work in the English notation, which is an inverted version of this diagram. Okay, so to, sorry?
Isn't this the Russian one?
Yes, this is the Russian one.
So your statement about the scaling was about the boundary of that.
About these. So here, if you denote it by x and y, or in the rotated notation, if you denote one axis by u and the other by v, then the v of u determines your boundary shape.
And that curve has some specific form. That is the.
Yes, that curve has this specific form. This is what this Vershik-Kerov and Logan-Shepp showed.
And the boundary of mod u is 2 is this line.
Yeah, so after a certain point, this boundary just coincides with this horizontal and vertical axis.
Sorry, I think Shiraz asked this question that if you use that Markov process with that probability, then is it that asymptotically it settles down to some probability distribution, which is given by the probability of that Young tableau? Is that the point?
No, I didn't understand the question. Can you please repeat?
So, a Markov process can lead to, an equilibrium distribution.
Okay.
So, in that case, you will have some distribution of Young tableaus in
Right.
the final
Right.
thing, and that would be given by some probability distribution. That would be the asymptotic probability distribution.
Yes. Yes.
And is that the same as what you mentioned as the probability of a Young
Yeah.
tableau?
Yeah. So as we go to the large and large number of boxes, so all these Young this growth process converges to a particular Young diagram, which has this particular boundary, the limit shape. And I'll show that if we find out the probability of this particular shape, which I'll show from doing the saddle point analysis of the partition.
It goes to single Young diagram, or does it
Yeah,
go to
all the, like you go to a large k limit, so all these Young diagrams, their boundary will look like this. I mean, this will be the only boundary which remains invariant under the scaling. So in the large k limit, all the diagrams, the boundary of all the diagrams approaches this limit shape.
So it should be some statement like the measure is peaked at this shape. Not, is it all the diagrams?
Yeah.
The most likely.
Yeah, it's the dominant configuration, we can say, and if we try to find out the probability associated to this configuration, it turns out to be almost equal to 1.
But this probability distribution is not the same as lambda k square divided by factorial k.
No, that measure associated to this particular, the diagram with this particular boundary is nearly equal to 1 in the large
I
k.
can get this diagram by doing the following thing, that I just look at the maximum of that probability distribution.
Yes,
and
yes.
Look at what that Young tableau is.
And that turns
And
out,
that's this.
yes,
Yeah.
yes.
And how many boxes in the kth row are there in this distribution?
How many books? K is a total number.
Sorry, the nth row. So suppose I want to know how many boxes there are in the nth row. Maybe I should ask by the m, where m is of order square root k.
Okay,
So let m be equal to alpha square root k.
okay.
Then there's some formula for how many boxes. This thing has a shape, right?
Yes.
So that's this thing. So I just can't understand this U business. What does it translate to in terms of?
So if
Boxes
oh yeah, we'll see the relation when we go to the matrix model.
Okay.
Sort of related to what you said. M row will correspond to, U will be a function of M. That's it.
Yeah. So it's like row plus column and row minus column, something.
Yeah, you will be you will be related to the number of boxes.
Right. So like there are V boxes in the UX row. Is that
V boxes in the UH is related to. Oh, no, it's the other way around.
Like
is the other way?
And this property is specific to some particular group. You said SN, but
No, this is independent of the underlying group, but for the yeah, I mean
So what is
you.
the underlying group?
I mean, if you take a representation of say SUN group, then you can write a Young diagram corresponding to that representation. But you can also consider that Young diagram as a if there are k number of boxes, that Young diagrams also corresponds to a representation of SK.
So now are you talking about a different Markov process having to do with the Plancherel measure associated with SUN?
No,
And that also is that what you just said? What do you mean by underlying group? Because so far there was no group underlying anything.
yeah, that's the point. Yeah, like I have not talked about any group
and
here.
for that group, what are the allowed Young diagrams? Let's say SUN that has some constraints on the structure of Young diagrams, and then you can ask the question that if I increase the number of boxes at large number of boxes, what is the shape? This is a clear question, and is it dependent on where you started with? You know, which Young diagram you started with, and then you increased. Is it Markov?
Are you
First
asking
of all,
where
is it Markov?
does Plancherel measure peak for SUN for large N?
That you can ask, but more important question is probably is it well-defined question? Is it that it depends on the path how you go to large number of boxes? First claim is it Markov, it does not depend on it. Then the answer is that it peaked around this distribution.
Sorry, and one last. Can you draw that peaked tableau in the normal way, please? Just
This term.
yeah, just on the board.
Okay, so
Rows and
this.
columns.
So this diagram.
Can you draw it so that it's normal tableau? So
Oh,
rows is-
okay. Sorry.
And not upside down tableau, just normal tableau.
Okay. So it should be a symmetric tableau. So if you look at the boundary of this, it should be.
So it has a maximum row length and a maximum column.
Yes.
And that maximum row length is that mod is about 2 square root k.
Yes.
I see. Same as the maximum column length.
Yes.
I see.
Okay. So to write down the partition function, we can define this Young lattice by taking the Young diagram, all the Young diagrams at each level. So by yk, I am denoting all the Young diagrams at level k, and so all the Young diagrams in yk, they have the same shape but different, same number of boxes but different shapes. So we can think of this as a canonical ensemble of Young diagrams with the same macroscopic variable k, and we can consider this Young lattice as some grand canonical ensemble, so that we can write down the partition function. So the Plancherel measure is given by this expression, so the partition function looks like this. And this partition function is solvable in the large k limit, and in that limit the partition function is dominated by a single Young diagram which has a boundary shape exactly same as the limit shape.
Can I ask, if you restrict the allowed Young diagrams to have at most n rows, let's say, then you can ask a similar question.
Yes, yes. So
this looks like so far it's leading on a large n, it feels like, because you are allowing for all Young diagrams.
yes.
But finite n you probably will.
Yeah, so finite n means if you consider the representations of SUN, then there will be a bound on the number of rows you can have. So what will happen is in anyway in that case also you will be studying the large n limit, so n goes to infinity limit. But as I will show that this partition function is similar to the Gross-Witten model, and we can see it easily from there, that after this number of boxes or the number of rows crosses n, there will be a there will be a phase transition, and then this growth process is not, I mean then this growth process is not valid there. This growth process holds like up to n, you will get, so you see if this is n, then this shape will be something like this as you go to the large n limit. Once you cross this, then this thing doesn't work.
But is it true that you can also ask, okay, I'll not ask now. You can ask that if you take 1 by n corrections, is there also some sense of Markovian property that leading 1 by n corrections?
Yeah, when I'll talk about the fluctuations.
What is partisan function? Can you explain the partisan functions once? What does it count?
So,
It's reading Young diagrams by N by K. K is like the energy.
There is the grand canonical partition function.
Yes.
Principally, you could consider a microcanonical thing where K is something given, and you are looking at all possible Young diagrams with that thing, which will be given by presumably your Plancherel measure for.
but as we are going at higher and higher,
yeah,
then
it's
the number of
continuous.
boxes is changing.
No, actually, so you're doing some time update, right?
Yes.
So from K you are going to K plus 1,
Yes.
blah, blah, etc., etc.
Yes.
So after 1000 updates, you will always have K plus 1000 boxes. So your K will be something given at the time.
Okay.
So any
So
number of updates at any particular time, you don't have a variability in K.
Oh,
Because
so
K
you're
is
saying in the asymptotic limit or in the k goes to infinity limit, we can think of this as a microcanonical ensemble. Is that what you're saying?
At any particular time, the distribution is only over things with a particular K, because K is your time. So,
Yes, k.
however,
Yeah,
for counting purposes, as usual, you can introduce a microcanonical answer. That's what you've done. You see the delta K minus
Lambda K.
etc. That saved Yk inside. That is what I would call the microcanonical ensemble. And then you are, sort of giving a chemical potential for K.
Okay.
What does P lambda K looks like as K is taken to infinity? It is e to the power K log K, roughly e to the power K log K. This is like density of states. P lambda
P
K,
of lambda k is the Plancherel measure, this
yes,
measure.
If you can take the dimension of lambda K, which is a known function.
Yeah, dimension of lambda k is just the number of standard Young
number.
tableau.
So if you take it at large K, how does it look like? Is it exponential, or is it K log K, or is it less than e to the power K? How does it look like? How does it go?
Yeah.
Why should this be independent apply?
No, it depends on the representation also. With symmetric, it will go like 1.
Right.
But
If it is antisymmetric also, it will go like 1.
sorry, I thought you had.
Even for large K, the dimension of totally symmetric is 1.
Right.
It doesn't,
So it's not
so you have to see the diagram to see what is the large K limit.
Sorry, wasn't the sum over lambda K of that quantity, wasn't that equal to 1?
Sum over lambda k of
Of lambda K square over K factorial?
yes.
So why isn't this QY something very trivial? Why is it just, yeah, 1 over 1 minus Z?
Sorry, I didn't
Yeah,
get it.
that seems to
So
be
the,
1.
the
Suppose
sum
I-
over lambda k, yeah, this
Suppose in
is
that
1.
box, at first do the sum over lambda K,
Yeah, that's
then I
1.
get 1 for every K, right? For any
Right.
fixed K.
Okay, so then you're saying that this
This is
just
ZK,
z
sum over
k.
K is that right? Just 1 over
Yes,
1 minus Z?
yes. Then I probably what he said is
Yeah.
then because then it is just delta.
IIT Bombay?
Yeah, it's
there is
delta
some-
K
there
minus
is some-
lambda K.
Rama, there is some noise coming from your end. If possible, when you are not speaking, can you try to see if the mic can be turned off, because there is some
Okay.
feedback
Okay.
noise coming.
Yeah.
Thank you.
Huh? Can you hear us?
Yes.
You made all of the states degenerate. And
part I can't understand.
So
I agree.
it's, so this,
Yeah, the delta function of
the delta function is, it's just to make sure that, like, it just says that the number of boxes in this representation lambda is
and then
k.
you're summing over k.
Yes.
So that whole sum there, isn't that one? The sum, the last sum.
This sum.
Second sum looks like will be 1. Yeah, because it's sum of probabilities, no? It should add up
Yes,
to 1.
it should add up to 1. Yeah, that's, so I'll look into this. And okay, so we can do a large K analysis of this partition function. This is the formula for the dimension. We can define these variables HIs which are given in terms of the number of boxes in each row. So in the large, the large K limit, the partition function takes this form with this some effective action. So then we can write down the saddle point equation, and this is how the equation looks, with this parameter xi is related to the parameter z and k prime, which is the renormalized number of boxes, and here UH is the Young diagram density, which we define as del x over del
You
x.
just went a bit too fast for me. Could you go back one more slide? What was that? HI is the what?
HI is, these are the hoop numbers related to the first box. So you can just, so that it is just to make sure that these variables are always in the decreasing order, they're strictly decreasing order.
Ni is the number of boxes.
Ni is the number of boxes in each row. So
Okay. So that's some famous formula for the representation of.
yes,
For the diamond. Okay.
yes,
Yeah.
And you know how S effective looks like, right?
yes, I know.
And then finally, it's written as a functional integral over h of x.
Yes. So I'll write down the partition function in terms of these variables HIs.
And what is written this QY?
This QY is the partition function.
Okay, so it's a probability distribution. But then if you now weight with some Young diagrams, then it becomes non-trivial, right?
Wait, what? Sorry. No, the measure is only this Plancherel. This S effective has some other action? Other action?
No, it's
it's
weighting
the
over all, summing over all possible Young diagrams. But now suppose you wanted to find the expectation value of the number of boxes in the ith row.
Yes, expectation value.
Now you can use that probability measure
Yeah.
to get something non-trivial.
Yes. But not this quantity.
Not this quantity. This quantity is 1,
Yeah.
but you can use it as a probability measure.
Right. Yeah. Sure. Yeah.
Somehow, don't you want your partition function to count how many states are there corresponding to k boxes? That will be like degeneracy. This is what you want to put, and times energy, which is yet to be k.
Yeah, you could have done that if you got rid of that 1 over k factorial in that formula.
Yeah, I think this would be, this makes sense very well. Right?
Yeah, but I don't know what they're after. I think they're after a probability distribution.
Yes.
They want something that is distributed to 1.
Yeah, but if it is only a probability distribution, where is the e to the power minus beta h?
The beta h, yeah. So
it should be like a beta equal to 0 kind of case. Sorry, excuse me. Yeah. So that, again, it just becomes the,
for each k, it's a probability distribution,
yeah.
and then you're getting sort of like you're weighting over probability distributions. You probably will, if you want to get a probability distribution, you'll probably eventually divide that by 1 over 1 minus that. You can renormalize that other probability distribution. Right? If you want to compute something about the impact, that then becomes reasonable, right? Because it becomes a reasonable
Then
probability. It just requires a second normalization.
That's two things. What is the probability that you have k boxes?
Yes.
If you have k boxes, what is the probability that you have lambda?
Exactly.
Now, the second probability is the probability that 0.
And that is the probability for which, yeah, exactly.
Now, probably you want the first probability to be non-trivial as well if you want to keep all the information.
Yeah, and you want that to be z to the power minus k, she said.
Then the partition function is trivial as you said, right?
It's trivial, but it's trivial as a number. But now suppose you want in that ensemble,
What is the contribution from various sectors?
yes, then it's not trivial, right? It's a non-trivial probability
Yeah, we can do that for Chern-Simons theory as well.
For instance, yeah.
Okay, so now
What was your K? I'm sorry, what is K?
K was the number of boxes. So now we are going to the large K limit. So
What is L?
L is this some large number. The boxes are distributed up to M, and then the boxes in all the rows up from M to L is 0. This is some large positive
Any large
integer.
number?
Yes.
Any large number?
Yes.
And Z is like temperature. Like if temperature increases, then Z increases.
Z is what we call in the grand canonical partition function the fugacity.
And it will increase if temperature increases. You are taking L on this side as well, L number of rows, or L is just for.
So yeah, you can consider, for example, say a square box of side L, then the area is L square. This is some large number, so you're going to the large number of boxes limit. Then the number of boxes in this particular area will go like L square. So this is just to take the large number of boxes limit.
L is like square root K.
Yes. Okay. So now we would like to find out the solution for the saddle point equation, but while finding out the solution, what we have to keep in mind is that any two Young diagrams which are related to each other by transposition, the probability associated to them is same. So the solution that we should get for this equation must be a symmetric solution.
Are you producing this Vershik?
Yes, yes. So there does exist a symmetric solution of this equation, which is given by this expression. This UH is supported in the interval P from P to Q, where P and Q are have these expression. And now since P is greater than equal to 0, this means that the solution is valid for xi between 0 and half. So also there's this condition which that xi square has to be k prime. So from the definition we see that this solution exists for either xi equals to k prime equals to 0 or z equals to 1.
H is a proxy for V.
Sorry?
H is a proxy for V. You had U and V.
No, U is related to H. Here this UH is the Young diagram density. The U that I wrote earlier in the limit shape, that is a different U. That is just if I rotate this diagram, then this is my V axis and this is my U axis. So the boundary shape is given by V as a function of U.
Yes.
But here the UH is what I have introduced. It's just del x by del h in my variable. So I define these h variables. Then I define this x, which is just I over L. I define this continuous variable. So here U of h is this Young diagram density which I have defined.
Where, sorry, so what is U of O? Where did U come from?
U of h.
Yeah.
So this is what I have defined.
Oh, I see. I see. It's the density of H is.
Yes.
I see.
Yes,
It's high value.
yes.
But knowing U of H, you should be able to figure out V of U.
Yes, you can.
Should be, right?
Yes, you can. Okay, so we have these two possibilities, but if we consider this case, then this means that there is no box in the Young diagram. So the non-trivial solution corresponds to z equals to 1. So it can be checked.
What was the zeta, please?
So zeta is this variable related to z and k.
Sorry, so it's a little bit more detail if you can. So that S effective of H, how does it look like?
Oh, S effective. So actually, this is not this has a long expression. I
So
don't.
you would apply Stirling to all the factorials.
Yes,
to the
yes.
team L and blah blah.
Yes,
And then your Plancherel will be something.
Yes.
And so on. So I see. So it's not easy to write down. That
I mean, I can write it down, but then I'll have to do some calculations. I have the expression, I can
So
show
when
that to you
when
later.
hit the limit of n, you know, you're saying that there will be some phase transition. When
Yes.
your number of basically you're doing representation theory of Sn. So
Yes.
therefore, clearly, you know, your number of in the what you call English.
English
Your
representation.
the number of columns cannot go beyond.
Beyond, for SUN.
For SUN or Sn, the same thing.
Yeah, but if we are studying this process for the symmetric group, then we can go on and on. There's no restriction on the number.
Yes, absolutely correct. SUN. So, how does one see that in the mathematics of all these numbers and etc. That there's something funny happening?
So far she's not put it. So far she's just doing Sn.
Yes.
She'll have to give us a new rule when she does the rest. So far her rows are not covered.
Okay, so we'll focus on this solution corresponding to z equals to 1. So for any value of xi between 0 and half, it can be checked that the Young diagram that we get, that is always symmetric under transposition.
I'm really sorry to slow you down so much, but you said for some values of xi there was a non-trivial saddle point, and some others there was not. Is that
This is the restriction. There's this condition that xi square has to be equal to k prime. So and xi square is by definition z k prime. So the solution to this equation is either both of these xi and k prime are 0 or z equals to 1.
So only z equals 1 has a non-trivial.
Non-trivial solution.
Oh, so this partition function
Is
sort of
1.
only has a reasonable solution near z equals 1. When you weight everything equally, basically.
Yes.
So, on another word, that partition function q of y she wrote is 1 by 1 minus z. When z equal to 1, it goes to infinity, no?
So can you please repeat?
So, the q which you wrote, q of y, is technically 1 by 1 minus z, right? It is summation over k z of k. The rest
Yes.
of them are 1.
Yes.
So, when z is equal to 1, it goes down.
Yes.
So, maybe z equal to 1 is the one which you are contributing.
Yeah.
Z equal to 1 closer, yes.
Okay.
As Abhijit just said, I mean, since you've normalized your probability so that each k contributes 1, if you want large k to contribute, you better take z to 1.
Hello?
Right, I mean, that's physical.
Yeah.
Can you hear me?
Yes, we can hear.
Just one comment about the partition function here. I mean that number one position, that is sum over diagram for a given shape. Dimension lambda k square by factorial k sum over lambda k for a given shape is 1. But here the sum is over all diagrams with box number k. Even if I stick to box number k, there are different shapes. If you stick
Oh,
to
I
a
think-
particular shape, then dimension lambda k square by factorial k is 1.
Yeah, so I think what he's saying is that if you take if you consider all the Young diagrams with number of boxes k, so you have different shapes. So and corresponding to each shape you have various Young tableaus, the standard Young tableau. So the dimension is the number of those standard Young tableau, and if you take this sum for the particular value of k, it is 1. But here the sum is over all the k's. That's what he's saying.
Yeah, but if you do weight the sum k by k, so then we can first do the sum over all boxes with a given k, then get 1, and then do the
Then
sum
we
over
can
k.
do the sum over k.
So, both are equivalent.
So do you agree?
Have to sum over steps.
Yeah, I mean, I agree that it's a non-trivial probability measure over shapes.
Okay, so the limiting value, which is half, for this limiting value the distribution is given by
The limiting value is zeta equals
So because I said that this solution is only valid for zeta from 0 to half. So the maximum zeta xi can go up to is half.
With z was always 1, but what is k prime?
K prime is just the number of boxes divided by L square. So this is some sort of renormalized number of boxes.
L was something completely just put in by hand, right?
Yes.
Order one number, some order one number.
Okay, so it was put in by hand in your definition of that h.
Yes.
Okay, so it's just some fake thing that you put it in and then you vary that to vary zeta as z. So z is always 1, but the
Z.
zeta changes.
Yes.
Why are you doing this L business? Why can't you choose it?
Yeah, we can also choose this M. I mean,
Okay, fine, but somehow convenient.
yeah, for say if you are
Phases will depend on choice of zeta. Zeta between this and this, you will have this phase.
Well, your original measure was just over young time. L is something you put in by hand, right?
Yes.
It's just totally
yes,
in your
yes,
head.
yes. We could have taken M also.
A equal to let's say 2 times square root k.
Let's
Doesn't
see.
matter, fix
Right.
it. Now the mapping between z and xi is you want one. So basically your phases will be leveled by xi or z or temperature, whatever you.
Yeah, but physically there was only one value of z. What was it that you're blowing up z's near 1? You see, you told us 2 things. First you said that only z equals 1 is physical, as a non-trivial thing.
Yes.
But now you seem to be getting many different answers depending on the xi.
Yes.
This is what I'm trying to understand.
Oh.
Yeah. Perhaps what you're doing is taking 1 minus z and blowing that up. Is that what you're doing?
No. So you'll see that as he was saying, that k is some sort of a time parameter which we can associate. That the Young diagrams are growing with k, but I'll show that the xi parameter here is related to k, and it is actually that parameter xi which plays the role of time.
And so these different solutions you're showing us are physically inequivalent. They'll have different values of square root k, for instance. I mean,
Yes.
Different
Yes.
shapes,
So
right.
this solution for any xi, so xi varies from 0 to half. So between 0 to half, for different values of xi, you have all the diagrams which you can have at any stage of this growth process. And xi equals to half will correspond to your asymptotic limit when the boundary shape becomes the limit shape. So the xi parameter is characterizing the diagrams at the intermediate stages.
But I'm really sorry to bother.
I think, sorry, if I may. You take time to be of order square root k, you scale it, and now with that rescaled time, you look at the dynamics. And now the claim somehow is that the rescaled time range is between 0 to half, and then there is some dynamics associated to that. The probability peaks at a different shapes, and that shape at the final time, very large time, which is namely. So even for times of order square root k, but not very large, you would still have non-trivial saddles, and those saddles will approach this limit shape in the.
But I don't understand where in the mathematics any dynamics has been put in. You were just doing the equivalent
The
of
dynamics is just the k. I mean, I'm taking k to be the time.
So is it right that what you're doing is effectively taking your suppose we should have weighted not by z to the power k, z to the power whatever number of boxes,
Okay.
but number of boxes scaled by some large number. And what you're doing is taking a scaled z variable. Is that effectively what you're doing?
Yeah.
Scale z variable,
Yeah.
which is like as you said, 1 by 1 minus z is large.
Yeah.
That is scale variable.
Okay. So you're allowing the number of boxes to be large, but how large?
And you expect if that is very large, then you get this universal distribution.
And there is a scaling that you have done somewhere in the middle, dividing that zk prime, whatever that stuff.
Next slide.
Yeah.
This.
Psi
Yeah.
square is equal to zk
Q.
by L.
So yeah, this when we go to this large L limit, we have defined all these variables. So the number of boxes is the sum of all these ni's. So if we write it in the larger limit, it will turn out to be something like this.
But large or small compared to what? There's only one in the game, right? There's no other number. Any number that's large compared to one is large, isn't it?
Large in the sense that factorials need to be approximated.
Okay, so once we got into what, thousands, very good.
Yeah.
Okay.
Values of the order.
As long as you can talk about continuum shapes, you're always large. I mean, if you can no longer see the discreteness, you're always large.
Yeah, but in that continuum shape, you can now study how it behaves with time.
But this is what I'm wondering. If it's only characterized by number of boxes, once number of boxes is large compared to one, there's no other scale in the problem.
So everything is weighted by z to the power k. So if I write down an action, it becomes z to the power k log z.
Okay.
Now k is made into a coupling constant so that L square sits outside. So it's really the coupling constant. Now your zeta square becomes your coupling constant. You change that, and with respect to that, you're looking at different solutions.
Excellent. So now let's take the end point of what you're saying. You're saying I'm looking at an ensemble dominated by a large number of saddle points. A large number by a young number with a large number of boxes. Okay. Now I want to understand what large is. There's only one number in the problem, which is 1. So if you're large compared to 1, that's needed anyway to have this continuum description. After that, there's no other scale. So what are these different sets of solutions?
They'll be parameterized by this z, right? What is zk by L square?
That's right. But I'm trying to understand what
But-
it is.
but-
Suppose number of boxes has to scale like, let's say, some, your number of boxes is like k.
What is k? K is now just some artificial number put in your hand, right? In your original problem, there was no number.
There was no number, k is some given number, and I am going to study the behavior of the theory as k goes to infinity.
Good.
And now I am also, k is some given number which is a leading order behavior near k equal to infinity. And then we are trying to see what are the contributions that are largest in the partition function.
Yeah.
And those contributions are largest as j is near 1.
Yes.
So 1 by 1 minus z is scaled with k in a manner, let's say k to the half or some suitable power.
Yes.
And that scaling has a coefficient.
Okay.
So should consider the number 1 by 1 minus z in the units of, let's say, square root k. That is the number. That number could be 0 to 1. And according to that number, you can have different phases.
This
How
is
close are you?
similar to the large and limit of the gauge theories, and we'll see that this partition function is exactly same as the Gross-Witten and Wadia. So so this large k limit is just equivalent to doing the large n analysis of the.
I understand large k, but what you're doing is getting one parameter set of solutions.
Yeah, I think instead of dimension k there with the factorials, just write down whatever is obtained by Stirling's approximation.
Yeah.
Okay, now you say that's not justified. Well, it's justified if you work in terms of not h's in the case, but somebody scaled versions.
Yes.
Okay, but still it's a finite thing. I'm not
Yes.
taking any infinite limit.
Yes.
I'm just taking them to be large.
Yes.
Compared to order 1. And now you can still now solve the problem, right? Now you can solve the problem as a function of some parameter that multiplies this large number and take that parameter of the.
Yeah. Hello?
Yes, yes.
So even in the large scale, you got to figure out there's a graph of diagram which dominates the partition function.
Yes.
Even in the large k unit, there is a class of diagram which is all those diagrams are parameterized by the value of this guy. So what you can show is that even in the large, when the box number goes to very large, then there is a class of diagram which estimates the partition function or dominates the partition function, and that parameter, that class of diagram is parameterized by xi from 0 to half, and xi goes to half also the limit shape of Kerov and shape what they have to follow.
Okay.
Can I say one
So
sentence?
all these diagrams parameterize
Now,
one
you
number.
say that and then let her go.
Yeah. So consider the following order one number. Call x is 1 minus z times square root k.
What is k?
K is the number of boxes. We are going to study the whole problem in k going to infinity limit, and we are going to consider the leading order results.
I thought you either specify z or specify k. You don't specify both.
I am not going to specify those. The statement is I am specifying k, but then the contribution that dominates. So now all the x's are valid, but then some x's dominate the most. The claim is that the x's that dominate the most are given by the following formula. X is 1 minus z times square root k. This is an order 1 number. So z is very near to 1 and it's scaled like 1 by square root k. So their ratio is order 1 number, which is x, which is their xi. What is wrong with this statement?
I don't completely understand. But let's go on. Yeah, we'll after that.
One thing I don't understand. Why are you telling that the partition function is 1 over 1 minus z?
Go to the bottom.
Yeah.
So in this
That-
sum here, Shubhankar, can I perform the lambda sum first? Lambda k sum.
But that's not 1. That's what I'm telling you.
Yeah, that's 1, right?
So that's not 1.
Oh, it's not 1. So how is that?
Lambda sum will give you number of boxes, number of diagonals, number of shapes for a given k.
Number of shapes, but number of shapes weighted with this factor, right? Dimension lambda k whole square divided by k factor.
See, what is 1 is after you see the shape. After you see the shape, then you sum over. If you that all sum over all possible diagrams for all possible tableaux for that particular shape. So I should what you are calling 1, that is
But there is a sum
that
for
is
step
the
which makes it 1.
sum over tableau for a given shape which dimension lambda pixel by factorial k is 1.
But z
But
k
we
is
can-
independent of shape, so there is a sum over shape as well.
Sum over? Yeah.
Shape to the k does not depend on the shape. So
Okay, so function you can write k equals to 0 to infinity z to the power k times number of diagrams for a number of shapes for a given vector.
Sorry, what is a shape and what is a diagram? Maybe is it labeling the things inside with the numbers?
No, shape is if I give you a particular shape, there are different possible Young tableaux.
What does that mean?
But in other words, if I give you a particular diagram, there are different possible Young tableaux.
So if you take a particular Young diagram, so you can label these boxes with numbers, but the numbers should be increasing along the rows and along the columns. So the number of ways you can arrange these numbers is gives you the number of standard Young tableau.
Yeah, and that number is equal to.
That number is equal to the dimension.
Yes.
Yes.
The number is equal to dimension k square by factorial k.
So then that quantity is associated with the shape.
Yes, that quantity is associated with the shape.
So now we are summing more shapes, right? That sum, the second sum is our sum more shapes.
In this expression, this sum is all possible diagram. This sum is all possible
So
diagram.
this lambda k is also a set. So at each level k we have different shapes.
Fine. But the sum over shapes gives
Shape.
1, right? For fixing the number of boxes.
Yes, we can do the sum first over each of these shapes.
Sorry, are you saying the sum over lambda k is not sum over shapes, but sum over shapes with a bunch of numbers in them?
Oh,
So that would just give you an additional factor of dim lambda there.
yeah.
Because it's region, right?
So what is happening is we have all these Young diagrams with different shapes. So and corresponding to each shape we have a number of Young tableaus. But when we are writing this partition function, we are not summing over the tableaus. We are just summing over the
Talk about shapes and what is a tableau now?
tableau is if say you put these numbers. So these are increasing along the row as well as along the column. So the number of ways you can write such numbers in this tableau. So you pick a set of numbers, say I have chosen up from 1 to 11. So you have to just make sure that these are increasing always along the row and the column, but you can put it in different ways. So those are,
Way is called tableau.
yeah, each way is called a tableau.
This whole thing is called shape.
Yeah, this whole thing is called shape.
Okay.
So
now
the sum is over the sum is over the shapes, and this sum dim lambda k square over k factorial, this is equal to 1 when we sum over the tableaus. So we take a particular shape.
So effectively that's one factor of lambda k less, right?
No, but we checked it with K equals
Yeah, we
3.
checked it.
We checked it with for S3, and summing over tableau, summing over shapes gave 1, right?
Yeah, so
Because S3 had 3 representations, two one-dimensional representations and 1 two-dimensional representation. So 1 square plus 1 square plus 2 square, as Rama explained to us, was 6, and 6 divided by 3 factorial was 6. So when you summed over different shapes, we got 1 for S3, not over different tableau.
Sum over shapes, and for given shapes, sum over allowed representations is 1. You sum over both, then you get 1. This is what you did, right?
I summed over all possible tableau without any numberings,
Yes.
and associated with that with the shape, this factor dim lambda squared by k factorial, and for the case of S3, then I got 1.
No, but I don't think it will turn out to be 1 at each level.
What does level mean now?
The number of boxes.
Okay, but now if we do something else at S3, we won't get 1.
Yes. I think this is the report because I think it just associated to a shape, and the sum over shapes is true.
Yeah, S3 is large enough so that you can make a distinction between the tableaus and the diagrams.
Yeah. Otherwise, you will get a additional factor of half or something.
No, but both are commuting, no? Whether you sum up over k or sum up over lambda k, I don't think it is, it's not a sequence.
No, I think Shavankar, that was Shavankar, right?
Yeah.
So I think Shavankar was saying that the sum over lambda is not a sum over shape, but sum over, no, sorry, it's not a sum over tableaus, but sum over shapes. So, and the sum over tableaus, that is 1.
Yes.
But we just somehow for S3 think that it's the sum over shapes that gives you 1. Sorry, Shavankar, do you have to say something?
What does shape mean? What is the definition of shape then?
Shape,
What is the diagram I got?
yes, shape is a diagram.
And then sum over all the diagrams, right? For a constraint delta k minus mod lambda k.
Yes, yes.
That constraint will put you only horizontal 3 box, vertical 3 box, and 2 comma 1. What else can you get? The shape or the diagram, both are synonymous.
What happens is, for a given shape, you can have different tableau. Or whatever, for a given diagram, you can have different tableau.
Yeah, but what they're saying is, yes, so what they're saying is that for S3, even this sum over this measure for the different shapes turns out to be 1. So this is what. Yeah. Yeah, I think for, I mean, if we take some other k, I think it's not necessarily true that it will turn out
But
to.
here Naveen has made a very important point, is that the number of young tableaus corresponding to a young diagram, that is in fact a dimension of the representation of
Yes,
a particular
yes,
young diagram.
yes.
So this d lambda k square by k thing, if that d lambda k is actually the number, this is what Naveen is saying.
Yes.
The number of young tableaus corresponding to a young diagram.
Yes,
is
the dimension.
dimension of that
Yes,
sum.
and the sum over, yeah.
So in that case, if your sum is over young tableaus versus the sum is over young diagrams, there will be an additional factor of d lambda k in that measure.
Dimension.
So it appears that there isn't, because the S3 check works out.
I suggest we go on.
Yes.
Okay. Okay. Yeah. So for xi equals to half, this is how the Young distribution looks. This is the limit shape, and if we find out the Plancherel probability associated to this diagram, it turns out to be nearly equal to 1. So this gives us an alternate proof of the limit shape theorem of Vershik-Kerov and Logan-Shepp. Now, so Kerov also introduced a differential model to capture the growth of these Young diagrams, and he associated a time parameter to study the evolution. And what he showed is that the Young diagrams following this Plancherel growth process satisfy this first order differential equation, which he called an automodel equation, and all the diagrams belonging to this class are, he called them as automodel diagrams. And we can also check that with this, limiting value of the Young diagram density also satisfies this first order differential equation, which is very similar to the automodel equation of Kerov, where the time parameter here is mapped to k prime. Yeah, so now once we have the limit shape, so we can talk about the fluctuations of the limit shape, because the probability is nearly 1, but it is not exactly 1. So before going into the fluctuations, let's look at the Gross-Witten and Wadia model. So this is a familiar model to all of you. So if we write down the partition function of Gross-Witten and Wadia in terms of the Young diagrams, then the form is similar to the partition function that we wrote for the Plancherel growth process.
Just 1 minute on that, please. So you have trace you dagger, then what did you do from that step to that?
Yes, so we expand this exponential.
Taylor series expansion.
Yes, Taylor series expansion, and then we can use the Frobenius formula, and there are some identities relating this trace u to the power n to the characters of symmetric group, and then you can write down for this trace u and trace u dagger, it just we'll get just the characters corresponding to 1 cycles of the symmetric group, and then we can use this formula.
What is chi r 1t?
This is the character corresponding to 1 cycles, k1 cycles.
No, k.
So suddenly you're bringing
1 cycle.
Suddenly you're bringing in SUN representation here. R is an SUN representation.
R is the SUN representation, yes, but I mean when we start from here, so we can expand this exponential and we'll get some trace u to the power n factors, and there's a formula which relates this trace u to the power n to the characters of symmetric group, Sn.
I see.
That's it.
So
Actually, no. So now what you are writing is for the SUN model, no? Using the
yes, I am writing this for this unitary matrix model, but what I have in the end is this, the dimension is related to this character of the Sn group, but the sum here is over the representations of SUN. So this is the difference between this Gross-Witten and Wadia and the Plancherel process, and that's why the solution that we are getting, that is valid for a particular range of parameters. This partition function is not exactly same as the Plancherel growth. So we'll see that only we can map only the no gap phase of Gross-Witten and Wadia to the Plancherel growth, but not the 1 gap phase.
Yeah, I still have understood chi r 1k, please.
So
Yeah, chi r is a character in the symmetric group
yes,
of the representation r.
R, yes.
Okay, and what is 1k?
1k means that you are considering only 1 cycles of the symmetric group. So if you have say Sn, you have different permutations of these numbers. So if you have say 3 numbers, yeah, so then 1 cycle means just, so this corresponds to 3 1 cycles.
Identity. So it's that what representation? What represent like
Singlet.
Symmetric.
That's why it's the dimension of
The representation is R,
r?
but the element in which you evaluate the character is
let me say what
It's a
exactly.
dimension.
exactly.
That's
So
what she's
to
doing.
write the character table, Raj,
Yes.
Raj,
Yes.
to write the character table, along the column you put 1 cycle, 3 1 cycle for S3, then 1 2 cycle and 1 1 cycle, and 1 3 cycle along the column in the character table. So this 1 to the k is 1 cycle, there are 3 1 cycle. It's like an identity element of the permutation group. sigma 1 for the one cycle, 3-1 cycle. You
Ah.
understand what I'm saying?
I understand that.
And that is all she has written. Dimension of R of 1K is the first column in the capacitor.
I understand. Now I understand. Thank you.
Yeah.
Okay. Yeah, but there is a difference which she just pointed out, that here the sum is over representations of SUN group, while for the Plancherel growth we had a sum over representations of symmetric group. So, so because of this difference in the partition functions, we will see that we can map this Plancherel growth process only to the gapless phase of Gross-Witten and Wadia, but we cannot find out a correspondence between the one gap phase and the Plancherel growth process, because this model does exhibit a one gap phase also. Okay, so here's the idea of how we study the fluctuation. So since the automodel diagrams are mapped to the gapless phase of Gross-Witten and Wadia, so large n fluctuations of these classical solutions correspond to large k fluctuations of the automodel diagrams. And it is known in the literature that the classical solutions can be described in terms of phase space droplets, which are similar to the Thomas Fermi distribution at 0 temperature. Then these quantum fluctuations of these solutions can be thought of as small ripples on the boundary of those phase space droplets. So we will study the dynamics of such fluctuation, and we will see that the different modes of fluctuation satisfy an abelian Kac-Moody algebra. And we can then construct the Hilbert space and find a correspondence between the states in Hilbert space and the droplets in the phase space. And
this other thing, when you wrote down the partition function, each box was weighted by z, right? Because there was z to the k. There is no such thing here, is there?
no.
Here, all
Here,
the
no,
diagrams,
here this
there is no box
parameter,
counting parameter.
there is this parameter which is similar to z.
Yes,
Gross-Witten parameter.
this k product of k fundamental guys will give you the representation as k boxes. Yes.
Okay. So the approach that we take for the construction of algebra and its representation, it holds for no gap phase of a generic unitary matrix model. Here we will be concerned with only the gapless phase of Gross-Witten and Wadia, but it can be
This
extended.
because you don't want these things to grow very large, bigger than n.
Sorry?
You don't want these diagrams to go bigger than n.
Bigger than n.
The number of rows should not become larger.
Oh, for
And then this correspondence will.
yes, yes.
Because otherwise if you have W, that does not make
Right.
sense.
Okay. So I'll just talk a bit about the droplet picture. So the partition function of unitary matrix model has two equivalent descriptions, one in terms of the eigenvalues and the other in terms of the Young diagrams. And the relation between these two descriptions provides this phase space description. So we define this phase space density where these h plus and h minus are given by this function w, and the rho theta. Rho is the eigenvalue density and w is a function which depends on the matrix model that we are considering. So here I'll be talking about only the gapless phase of Gross-Witten and Wadia. So this is the w theta for that particular phase, and this is the eigenvalue density.
Wait, sorry, now eigenvalue is eigenvalue of the original unitary matrix?
Yes.
But in this new description of yours, you didn't have an eigenvalue, right?
In new
If you
description.
could go back one, this sum over Young diagrams, there were no eigenvalues.
Yeah, so now I'm just talking about the gapless phase of Gross-Witten and Wadia, and now I'm doing the analysis for this Gross-Witten and Wadia model.
Yes, I understand. But if you try to analyze the partition function doing it the way you did, then there are no eigenvalues in this description.
No, this is in the Young diagram basis, but we can write down a description in terms of the eigenvalues.
The more usual description is in terms of eigenvalues, and now you're going to give us a description in terms of both.
Yes.
Okay.
Yeah, I'm confused about high temperature, low temperature. So the phase that you are talking about in this model is you sort of like on the whole of the circle, which is low temperatures in some sense. But it felt like in the previous
Small e.
small a, yes, low temperature. If you imagine a is e to the power minus 1 1 by temperature. Okay. Now in the previous example, it felt like the large number of boxes will contribute at high temperature. This is like must be wrong, right? What is my mistake?
I think you should not directly relate to it like this because
Are you going to say that this gapless phase has a probability distribution that will be matching with the universal distribution?
the solution that I showed, this solution or this solution, this is exactly the solution, the gapless solution of Gross-Witten and Wadia.
This is why I am not understanding.
So
One of them looks like high temperature, one of them looks like low temperature. It must be wrong, but can you help?
yes, so when we are talking about this growth of Young diagrams and the partition function for this Plancherel growth, this is not a physical system. This is some sort of this is an abstract system. So the mapping may not be very direct. Okay, so given this function w and the eigenvalue density, we can find out the h plus and h minus. So here's the droplet picture for the for the gapless phase of Gross-Witten and Wadia.
Are you using Gross-Witten and Wadia or trace you? You have A trace you plus trace you diagonal?
No, I'm actually taking this one.
Oh, so the transformation changes the property somehow. From trace u plus trace u dagger to trace u dagger, you need to do an integration extra.
But sorry, this model has the saddle point is either uniform or gapped.
Yes.
You're saying you're working in the uniform phase.
Yes.
So what does it have to in the original model?
It's not a phase theory. So the uniform phase. It's because the equation of motion for trace u has a trace u dagger. Maybe later we should see that. Yeah.
So this trace u plus trace u dagger and trace u times trace u dagger, the base structure is same. Only this is your parameter sitting in front of trace u plus trace u dagger vector and beta, and the parameter sitting in front of trace u times trace u dagger is alpha. Then whatever phases you find, you will see that this phases are similar with beta equals to alpha times expectation value of trace u.
Yeah, that's right, except for the uniform phase, right? The uniform phase exists only in the trace u dagger model, and is not a
The
solution
phase
of the
structure of the two models is same.
No. Sorry. No, trace u plus trace u dagger at any finite coupling doesn't have a rho theta equals constant phase. It has a rho theta equals weakly phase.
For y equals to 0, you can have a constant phase.
For constant zero. But if you fix a given any non-zero constant, that's not a phase of the trace u plus trace u.
For non-zero line, you don't have any constant distribution, so this is the other distribution.
Yeah. So. Yeah. Right. Fine. So. But please go on.
Okay, so this is the droplet corresponding to xi equals to 0, which is circular. So this corresponds to a Young diagram with no box. Then for any value of xi between 0 and half, we have this sort of droplet. This corresponds to a generic Young diagram in the automodel class, and this is the limit shape, which corresponds to xi equals to half.
I'm really sorry to slow you down constantly, but I don't understand more now what's h plus of theta. Could you say again?
Yes. So we defined this phase space. So
Where did the phase space come from? How do you get something with
yes. So this is what they studied in the Datta and Gopakumar in 2007. They studied this relation between the eigenvalue between the eigenvalues of the unitary matrix and these parameters hi. So what they showed is that if you look at they showed is that there is a relation between these two descriptions, and from there you can write down this phase space density, so that if you integrate it over say h, then you will get the eigenvalue density, and if you integrate it over theta, then you will get the Young diagram
That
density.
is the defining property of H of theta of the space space. Is there some other definition, or this is what I've heard from you is there's some two-dimensional distribution, so that if you integrate it over one side, you get
Yes.
one, and the other side
Yes,
you get the
yes,
other.
yes.
That is the definition of this thing?
Yes.
Okay.
So these phase space are, this is in h theta plane, where h is my radial coordinate and theta is the angular coordinate.
That such a thing exists is not trivial. Okay, please go on. Later.
So this is defined only in the continuum, that is to say, when
Yes.
there is a continuum, a description available for the
Yes.
each of I mean,
But there is a relation also for the one gap phase. I mean, you can have this droplet picture even for the one gap phase or two gap phase.
but I mean large box.
Yes,
Only
large
when
box.
we have a large box, then you can introduce this conjugate.
Yes, yes. So the eigenvalues of these matrices behave like positions of fermions, and the variable h behaves like momenta. This is what they showed.
Where are the fermions? I mean, there's some physical fermions? Or this is just
No,
the
it's just a parallel that we draw when we talk about the unitary matrix model. If you look at the potential, it's a repulsive potential, so that no two eigenvalues seem to sit together. So we can think of it as so the fermions distributed in a one-dimensional.
Normally phase space is used for quantum mechanics, where there's some time. There's no time here, right?
Yeah, I mean, we can associate it to time. So as I showed this equation, if we look at the Young tableau density, it satisfies this dynamical equation where we can think of this parameter k prime as time.
Okay.
To call it a phase space, you should have a symplectic structure as well. Do you have all those things?
No, I do not know about that.
Yes, in Hilbert, yes. Hilbert, we will use that to quantize this thing, quantize this phase space.
Okay, so the fluctuations of this is the diagram or the droplet corresponding to the limit shape, and the fluctuations of limit shape can be thought of as small ripples on the boundary of this droplet. So as I said that these distributions are similar to Thomas Fermi distribution.
I'm sorry, where do you get the fermions from? I mean, normally these you guys, if you integrate, if you express them in terms of eigenvalues, etc., you get some van der Waals determinant, which
Yes.
will say that the eigenvalues are repelling.
Yes.
That will be Coulomb gas.
Yes.
It will not be fermions. Fermions will come only when you have these matrices which are functions of time. Are you saying that you are sort of going back from so you're bringing in the time dynamics somehow?
I don't think these are like or I'm not aware of that. These are not. I think this is just a parallel drawn between this because the phase space density that we have defined is it's a theta function. So it's constant up to some value and then it's 0. And this is how the Thomas Fermi distribution looks at 0 temperature.
But what does it signify? This W of H comma theta, where is this coming? I mean,
This is what we have defined.
fine.
I think to call it phase space is an analogy. Right?
Yes.
There's no precise notion in which it's phase space. Or anything.
But there are some works which relate these pictures to the some topological phases on string theory side. These are works by this Lin, Lurin, Maldacena and all those people. I do not know much about that,
In
but
that context, there is a phase space.
Yes, so LLM is quantum mechanics. That's the matrix as a function of time. And are you saying that it's not if you integrate out sorry I'm confused.
But she did talk about some sort of time.
I see.
Maybe the gauged the gauged quantum mechanics of the single complex matrix. When you integrate it out, you will get this double trace stuff. Maybe that's what it's like.
One harmonic oscillator, one adjoint harmonic oscillator gives you something like this, and then there was a phase space for that. Maybe that's it.
Yeah. It's like if I take your Torus Young's theory space, of course, in that case. But if I took weightage as a function of time and gauged it, yeah.
You will get more, you will get all of them, then you are restricting to small part, right?
No, I mean, I think
If you integrate it out, you will generate all multiplications unless there is some solution.
Right, that's true, certainly. There is further modeling.
Yeah,
But
further
that's the
options, yeah.
Okay. So if we now compare the phase space, this phase space distribution with the Thomas Fermi distribution, we can write down this single particle Hamiltonian density, where this function S and G are given in terms of H plus and H minus that I introduced. Then we can write down the Hamiltonian by integrating over the phase space. And if we find out the Hamilton's equation of motion, they turn out to be.
Sorry, what was little h of theta?
This is the Hamiltonian density which we are getting by comparing the phase space distribution that I introduced to this Thomas Fermi distribution.
Oh, I see. Fine.
So the equations of motion turn out to be those of a particle moving on a circle under the influence of some effective potential, and the phase space trajectory is given by this equation, and this equation determines the boundary evolution, how the boundary evolves with time. So now if we introduce a Poisson bracket like this, then we can write this boundary evolution equation in this form. So now to quantize these fluctuations, we promote these Poisson brackets to commutation relations, and then we can do a mode expansion of this boundary H theta, and we see that if we write down the algebra of these modes, it turns out to be a U1 Kac-Moody algebra. And if we further do a redefinition of these modes, then this reduces to this Heisenberg algebra. Then to construct the Hilbert space, we can define a ground state such that all these ANs annihilate the ground state, and a generic excited state is given by this. Now, so now we have the states in the Hilbert space. So each of these states corresponds to some droplet in the phase space. So to find out the shape corresponding to each state, we defined, we would like to define an operator which will give us the shape of those droplets. So, in order to do that, what we do is we first construct this the bilinear in H theta, which is in literature known as the Sugawara stress tensor, and the modes of this tensor T theta, which are the Virasoro generators, they can be written in terms of the modes of H theta, and a generic state Q of the Hilbert space is an eigenstate of the zero mode. And the eigenvalue is related to the number of boxes in the Young diagram, particularly this is k plus n square by 2, where k is the number of boxes. So for ground state, the eigenvalue of L0 is n square by 2, which means the number of boxes is 0. And so this is the shape operator that I was talking about. So I would like to find out the shape corresponding to a generic state in the Hilbert space. So if I act on a state, this operator, this will give me H theta, which will determine the shape of droplet in the phase space. So then we can write down the particular state
So
which
is it fluctuation around a given droplet?
Yes, so from this we'll get both the automodel diagrams as well as the fluctuations. So for this is a generic state which corresponds to the fluctuations of limit shape, and the number of boxes is given.
I'm really sorry, but what I'm imagining is this: I've got a particular droplet, then you're doing some quantization of the droplet, so there's some wiggliness in the
Yes.
shape.
Yes.
Now you had a way of associating a particular state of wiggles with a particular shape.
Yes.
What was that again?
So the state is any generic state in the Hilbert space.
Yes. And how do
So-
you make that a shape?
Yes, so we define this particular operator which we are calling as a shape operator. So if we operate this on any state in the Hilbert space, this gives us this particular shape. So I showed that the this is the equation of the phase space. So if you look at this shape, it is 1 plus 2 xi cos theta, which is the automodel shape, plus these fluctuations.
Plus those fluctuations. And those fluctuations were centered around theta equals 0. Why was that? Was theta equals 0 somehow special? In your model trace you dagger, there was no special point on the circle, right?
Yes.
Why are your fluctuations? Oh, it's probably this. Cos and sine. All your fluctuations look like they are centered around 0. Theta equals 0. I'm trying to understand why.
Yes,
I mean, how
it
to
is symmetric about 0, and that is because the you go to there are symmetry.
U goes to U dagger symmetry. I see.
Fluctuation of symmetric about theta equals to 0, that is because of u goes to dagger symmetry.
I thought there was no special point on the circle, so every point was the same. Maybe you're modding out by some. Maybe you're looking at those modes that have that symmetry. I mean, the original Gross-Witten and Wadia model has that symmetry. There's a special point.
Yes.
The trace you dagger problem has no particular center, right? You can phase U and phase U dagger the other way and it doesn't change. So you can rotate around the circle. It's a small point. Please go on right now. Later.
Okay, so the fluctuations of this limit shape has been under investigation in the mathematics literature, and what the results that they have is that the fluctuations of limit shape, they are given by a random Gaussian process, and the particular form of the fluctuations is this, which is similar to what we have got. But the difference here is that here these alpha n's are picked up from random Gaussian variables with mean 0 and variance 1, while we have only integer alpha n's. So we do not understand right now why this is happening, or what is the explanation to that, but we will.
So you have an ansatz. Your hope was that working out, taking the space-space analogy seriously would produce fluctuations of the independently well-defined fluctuations of the young dagger. And you're saying that it's almost working,
Yes.
but not quite. Okay.
Yeah, so in summary, what we have is a cleaner matrix model way to prove the limit shape theorem. We have a one-to-one map between the automodel diagrams and the states of CFT. Then we have a map between the Plancherel growth process and the evolution of gapless phase of Gross-Witten and Wadia model. But as the Gross-Witten and Wadia model exhibits another phase, which is the one gap phase, one can of course ask what kind of growth process corresponds to the one gap phase of Gross-Witten and Wadia. Then doing the analysis of the fluctuations, we saw that they satisfy this abelian Kac-Moody algebra, and the fluctuations of the limit shape, they match with the Kerov, Ivanov, Olshanki, these people have got, but there's a difference that the alpha n's that we have are only integers, and one can try to understand what is the reasoning or what is the explanation behind that. Then there are other measures associated to this growth process of Young diagrams. One of them is the Q-deformed Plancherel measure, and one can try to understand what is the matrix model corresponding to that growth process. So we are looking into this, and we hope to report on this one. Yeah, thank you.
Any questions at IIT Bombay?
No.
IISER Bhopal?
Shubhankar, do you have any questions?
I just want to say that vector quantization we are beginning to.
You are not very audible.
Audible.
Your voice is cutting off.
This vector quantization we begin for only for Logan phase, but I think it's more interesting to there for any other y gap or two gap So it's just one comment I want to make.
Could I ask Suvankar the question we had? Suvankar, is there a precise sense in which this object that you get, this object with h on one side and theta on the other side, is there some precise sense in which it's a phase space of something? And if so, what is it a phase space of?
So generic relation between the eigenvalue phi and the log diagonal phi. So if you take a generic, let's say you take a generic bracket model.
Generic what?
Placket one.
Placket.
Sorry, IIT Bombay, if you could mute the something.
If you take a generic model, one bracket model, okay, sum over a and a in the diagonal, and you can show that there is a generic relation between the h, the movements and the eigenvalue density. So it's not true. I mean, in the past paper, Rajesh want to show that there is a relation between the Gross-Witten and Wadia model. For Gross-Witten and Wadia model, there is a relation between the eigenvalue distribution and the Young diagram distribution. But later in some other papers, what we have checked that those kind of relations, the relation between the eigenvalue distribution and the Young diagram distribution is quite generic, and you can write that Gross-Witten equation for a generic unitary matrix model actually. So h theta or h plus minus theta, what she has actually shown that w theta plus minus phi rho theta. This is true for any generic unitary matrix model. So for a given any unitary matrix model, if you have different spaces, those spaces you can describe in terms of this x-ray droplet.
Okay, so you say that it's a very universal looking feature, but you don't have a clear identification of what it's a phase space of. Is this accurate?
Yeah, what actually goes on the actually the Coulomb gap. So because it's not the partial function we are considering, there is a usually time dependent. There is no theta dot or anything. But from this vector you can construct a Hamiltonian directly in terms of some h and theta. Okay, so this is what we get from this vector density. We get a effective non-particular Hamiltonian or Hamiltonian density is the vector Hamiltonian density is the function of h and theta.
Thanks a lot, Shivank.
Okay.
Thank
So
you.
we are starting on.
Bye.
Okay, any more questions?
Okay, I have just one. So this Kac-Moody algebra that you mentioned, so that relates to the ripples around a particular single droplet.
Yes, yes.
And so the single droplet is not the most generic configuration. So you can have multiple droplets.
Yes.
And there will be ripples around each one of them,
Yes.
which will be independent apart from some constraint about the total
Yes.
progress, etc. So is there something known? I mean, I have not followed this. It seems to be some kind of heavy duty literature using Kac-Moody and stuff. So is there anything known about multiple droplets?
Multiple droplet.
So you can have single. It's just if you are really talking about fermions, then there is no need for the fermions to be stacked up like in the just consecutive in the consecutive energy levels.
Yes.
So you can have the Fermi C, which will be like a filled droplet of the lowest energy, but you can scoop out.
You're talking about the multi-valued boundary of these droplets. So here for the Gross-Witten and Wadia, this
Yeah,
boundary is always single valued. So what you're saying is, I think, will correspond to the multi-valued boundary.
Right.
So if
Instead of H plus and H minus.
yeah, if the origin is not inside this droplet, yeah. So we believe that this can be extended to that case also, but we haven't really looked into that.
People have not looked at it already.
No,
in
no.
terms of discussing this stuff.
No.
Thank you.
Okay, no further questions, sir.
Okay, sir.
Okay, thanks. Bye, Rama.